Welcome everyone in my YouTube channel Educator Jeevan, and in today's video I'm going to talk about the gravitational force. This is the force between any two heavenly bodies, which is noticeable, but if you it's even between the smaller bodies, objects, which is very negligible to notice. Yes, in short, if you call about the definitions, it's simply the mutual attractions between any body, any two bodies in the universe. Whether it is a very big, like celestial bodies, or even for the small particles like an atom. And there are some facts about the related to the gravitations, before 16th century, there was a geocentric model was the popular one, in which the everything revolves around the earth. But after that, Nicholas Copernicus introduced the heliocentric, and which is about like the whole the heavenly bodies, planets, and each and everything are revolving around the sun in our solar system. And in 1687 AD, Sir Isaac Newton, he propounded the law of gravitations. And yes, this exists, and because of the gravitations, like our solar system exists, like universe exists. And next thing is you can see the tides on the sea, and this is because of the gravitational force of the natural satellite of our Earth, that's the moon. And you can see the effect much more pronounced in case of liquid than the solid. So the Newtons, he gave the universal law of gravitations, that is the force of gravitations between any two bodies. It's directly proportional to the product of their masses, the product of the two heavenly bodies, the masses of the product of the two heavenly bodies, and divided by, or which is inversely proportional to the square of the distance between their centers. So this is the law, and then we're going to prove that mathematically as well. Before that, I would like to introduce one PhET simulations, where you can go to the site or just phetcolorado.edu, and it's a free simulation from where you can really figure out, you can keep the different mass for M1 and M2, two different heavenly bodies. You can see there's a distance, and you can figure out how the distance and how the mass of a body can affect the value of gravitational force. You can play with this. This is a wonderful one, and I generally go on playing these things during my classes to the students, and it's really fun, guys. Just go through it. It's really nice one. So let's go for the mathematical calculation. As you know that there's here in the table, in the presentation, you can see there's two different mass. One is for capital M and one is for smaller m, lowercase m. And according to the law of universal law of gravitation, that's directly proportional to force, directly proportional to the mass, and inversely proportional to the distance between them from the center. So just put them together, and the proportionality constant is replaced by equal g, and that g is a gravitational constant. The value is 6.67 into 10 to the power minus 11 Newton meter square per kg square. And I will also let you know how to calculate the value of g in upcoming slides. So the unit of g, I think it's not big what happens here, I don't know, but the unit of g, it's like you can calculate it. I'll just show in the next slide. And like you can see the result. You can even try this one in the PhET simulations, or simply you can go with the like a mass. You can like what happens exactly when the mass is doubled, or distance, because in this case you are keeping the distance constant, this r constant, but the this mass is doubled. So what happened in the mass is double? In case of the capital M, there's 2m, in the small m 2m, so 2 into 2 4 times. So your force, gravitational force, will be multiplied or will be increased 4 times, 4-folds than the previous one. Similarly, you can see in the next slide, the one of the mass is doubled, but other again, the constant again here. If one of the mass is doubled, only the one factor will get doubled. Only this like 2 times. So the gravitational force will be doubled in this case. So similarly, you can try with the next condition when the object mass distance between the object is double and triple. So you can see down over here what happens if the distance is double. Your r will be 2r square or 2d, whatever you can use the letter for that. 2r square, it's like 4, so 1 divided by 4, which means like if the distance is doubled, let's say if it is 100, if you make it to 200, when you double the distance, the gravitational force will decrease by 4 times, by 4-folds. When the distance is triple, 3r, we'll take the square of 3r, that's a 9. 1 divided by 9, that means the gravitational force will be decreased by 9 times. So I have some table over here to practice for your brainstorming stuff, so you can do this. You can calculate mathematically yourself, or you can even try with this in the fate simulation that I have shown you previously. It's your choice. So now in the next slide, I'm going to calculate the value of small g, and that is the acceleration due to gravity. So as you know that F equals to g capital M small m by r square from the universal law of gravitation. And the next one, as you know that from the Newton's second law, F equals to ma. From here, if you replace the a by g, then you'll get the value g equals to F by m, and just simply substitute the value here and you'll get the gmr by r square. And if you talk about the Earth, let's calculate the value of acceleration due to gravity of the Earth. Then the mass of the Earth is this much and the variation is this much, and now you can insert the value over there and just calculate the numbers. You'll get the 9.8 Newton per kg, or it is even measured in meter per second square, so you can take either of them. This much for today. I'll continue the next sessions in the next class. Thank you so much.